This is Lab 3, Magnetic Field of a Bar Magnet. This lab determines the magnetic field to a small bar magnet and compares the measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the Biot-Savart law. Along with this, we will also create a computational model to visualize the magnetic field around a bar magnet. The Biot-Savart law says that at any point P, the magnetic field dB due to an element dl of current carrying wire is given by dB equals mu naught over 4 pi times I dl sine theta over r squared. Given a bar magnet with the magnetic dipole moment mu, if the observation location is on the same axis as the magnet, assuming that the distance from the observation location to the magnet is much greater than the separation, we get B is equal to mu naught over 4 pi times 2 mu over r cubed. And if the observation location is on the perpendicular axis of the bar magnet, and assuming that the distance from the observation location is much greater than the separation distance, we get that B is equal to mu naught 4 pi over mu r cubed. The Part 1 procedure, or the setup, includes downloading the magnetometer app on the phone, determining the direction of magnetic north by laying the phone on the table and lining up the phone so that the x component of the magnetic field is 0, laying a meter stick orthogonal to the direction of north, and locating the magnetic chip on the smartphone. For the on-axis dipole, the procedure includes finding a distance from the magnet to the sensor that produces a magnetic field with an x component of magnitude bx equals 20 microteslas, recording the distance and the value of bx in the spreadsheet, and then measuring it 3 times for accuracy. We'll also repeat this step for a magnetic field of 70, 120, 170, and 220, and recording the data in the spreadsheet as well. For the off-axis dipole, we will find a distance d perp for which the net magnetic field is 100 microteslas, and recording the component of the y component of the magnetic field, adding a second ruler perpendicular to the first one, and making sure that the distance d perpendicular is perpendicular from the horizontal ruler, and using the magnetometer app to determine the x, y, and z components of the net magnetic field, and then finally correcting the y component of the magnetic field by either adding or subtracting by from we will also repeat this procedure 2 more times so that you end up with 3 values of d and absolute value of b net. Some observations from this includes that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. The position of the magnetometer has an effect on the measured x component of the magnetic field. It's sensitive to objects that may also produce a field. And as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Here we can see the averages for all the on-axis distances as well as the graph of ln bx versus ln r. We plot the natural logs due to the fact that the distance dependence can be expressed by an equation in the form b bar equals kr to the power n, when k is a combination of constants and parameters such as a magnetic moment, which do not change during the experiment. From a plot of absolute value of b versus r, it is difficult to tell exactly what the experimental value of n is unless we use a curve fitting software. However, if we take the logarithm of both sides of the initial equation, we get that ln of bx equals ln of k plus n ln of r. Because ln of b of x and ln of r vary, but n is constant and also k, this plot will give us a straight line with a slope n and intercept ln of k. From this, we can see that the slope, negative 3.01, is very close to the expected value of 3. From this, we find the dipole moment to be 2.65 am cubed. For the off-axis analysis, we can extract the experimental values of B net, which gives us 1.6 times 10 to the negative 5 and 2.89 times 10 to the negative 5 teslas. We can model the actual magnetic field using a computational model. First, we create the magnet as well as the magnetic dipole. Next, we create a function to display the magnetic field. We then visualize the magnetic field on axis and perpendicular to the axis. Our output gives us that B experimental is 1.6 times 10 to the negative 5 and 2.89 times 10 to the negative 5 teslas, and B actual is 8.613 10 to the negative 6 and 2.5 times 10 to the negative 5 teslas. We can see that the experimental net magnetic field is greater than the actual. This could be due to the fact that the measurements were taken in a room, and so the magnetic fields of atoms such as microwaves or computers may have superimposed itself on this value. Now, what if we had an oriented experiment to compensate for magnetic north? By accounting for magnetic north, the x component of the magnetic field is 0. If this is not the case, then the magnetometer values would be skewed in the direction of magnetic north. What if we were to stick two identical magnets together and run the experiment again? Due to superposition, the magnetic field of the second magnet will superimpose onto the total magnetic field. This value would double, but the direction will remain constant.